Okay, so I will talk to you about a bit of some lead dating that we did on those two Apollo samples there, and why we think they might be connected to the Serenitatis and Crisium basin impacts. We have heard about that already a lot. So like we're interested in dating those basin impacts because they give us insights into the impact of flux recorded on the lunar surface for the first 600 million years or so after solar system formation or moon formation. And we have had various scenarios over time, like with one extreme being the lunar cataclysm scenario, where a lot of those basins form at 3.9 billion years. And on the other hand of the extremes, we have like just an exponential decay. And in the last years also, this lunar cataclysm scenario has been weakened by a lot of different arguments. And one of them is that a lot of the ages that are recorded by samples at 3.92 billion years might be connected to the Imbrium basin impact event. And the overview you see here is basically sample dates that fulfill modern day age criteria and have been linked reasonably well to basin impact events. And it's mainly based by on this review here by Nemchin et al. From 2021. And what you can also see is that apart from this 3.92 billion year signature, we also have some older samples. Anna talked about that already. And at 4.2 billion years, we have this one event that might be the Serenitatis event. And there's one sample, 67955, that has already been dated by several studies, the ones shown here in bold. And I want to show you some results that we have for that, and not just how we can date this sample, but how we can use our lead dating to also infer something about the origin of the sample. So the sample is from the Apollo 16 landing site. Anna has talked about the landing site in detail. This is the sample in question. Down here is the split that we worked on. And this sample is interesting because it is anorthositic norite, noritic anorthosite, depending how you look at it. It has flat rare earth or low rare earth element contents, but it has been suggested by one of those dating studies, Norman et al. 2016, because they looked at the trace element patterns in plagioclase and pyroxene, that the parental melt from which this sample crystallized was actually a creep ridge melt, which would connect this sample to the Procellarum creep terrain. So with this 4.2 billion year age signature might be connected to the Procellarum creep terrain. Now, to the work that we did, so we're doing a stepwise digestion of the sample, pulling out different lead components, chemically isolate them, then do an isotopic analysis of the isotopic lead composition, do some data reduction, and then we can plot it in a diagram like this. This is not yet the data, so this is just the evolution of lead on different solar system bodies. So you have the original lead from the solar system, beginning of the solar system, and then the lower curve is how the lead composition evolved on Earth, and the upper curve how it evolved on the Moon. And the different evolution curves are a function of the mu value. So this is 238 uranium over 204 lead. And so those evolution curves can be quite different. And when we then look at our data that we have over here, and we have an isochron, so the isochron in this diagram, the intercept over here gives you the age. You see 4.2 billion years. That lines up very well with previous published data. And what we can get out of this isochron as well is this direction that it goes towards. And this tells us something about the original the lead component that was incorporated into the sample at crystallization. And you can already see that this lead component must be quite different to the data point further to the right, which is the isotopic lead composition of the lunar magma ocean at time of crystallization. So in between those two events, the lead composition of the precursor of the sample has changed significantly. And if we model that, or just calculate it, we get a mu value of about 2000 that the precursor material needed. And if you have such a high mu value, that indicates the presence of a creep component. So with this data, we can verify this hypothesis from Norman et al. That indeed the parental melt of the sample was creep rich. And if it was creep rich, then that further supports the idea that this cluster of ages here at 4.2 billion years is it might be the Serenitatis event. The two data points is our lead age, and we also have a samarium neodymium age on the same sample split. So we have this age for likely age for Serenitatis, and close to Serenitatis we have the Apollo 17 landing site. And there is another relatively feldspathic sample from that landing site, 77017. So this has a very complicated history, but what we're trying to date here is this feldspathic, the whiter, brighter part. Sorry, gotta be careful. Yeah, and what we're trying to date here is at some point the sample was either crystallized from a melt or recrystallized, depending on which paper you're looking at. And this is likely related to a basin impact. And then what I want you to keep in mind is also that later there was an addition of a Mara-like component, which you can see there, the dark component. And just this diagram again, this is the data for the other sample. And if we plot in the data for 77017, we see we have a date that is quite a bit younger. So we seem to resolve a different event. And the initial lead component for this sample was very similar to the lead component of the lunar magma ocean at time of crystallization. What that means, between those two different events, there was not much change in the lead isotopic composition. And that indicates a low mu value, and that indicates likely that there was no involvement of a creep component. So the basin event we're looking at is likely outside of the prosolar creep terrain. Again, for this sample, we also have a samarium neodymium date, and now we want to find out more about this basin impact event. And what we did for this is we used this combination of this feldspathic rock type with the Mara-like glass component. We said, okay, if those two are together, they were likely together and then were hit by a smaller impact that melted the Mara-like component, attached it to the sample, and then transported it to the Apollo 17 landing site. And then Bajia identified different craters that are possible to create such a mix. And then our colleague Tian Lui used her impact distribution model to determine at the locations of those craters what is the most abundant basin melt from which basins. And what she finds is that it's mainly dominated by Serenitatis, Crisium, and Nectaris. And so we can make a probabilistic argument. So, but Serenitatis, we already say we think it's older and would likely involve more creep components. So that doesn't add up quite with the isotopic composition of the initial lead in 77017. So we think it's most likely connected to the Crisium event or maybe the Nectaris event. And then if we come to the conclusions, so with this first sample, we can back up that this 4.2 billion year event might be Serenitatis. The Crisium event also supports the older Serenitatis age, would also support that if it would be Nectaris. And altogether, such an old age for Serenitatis also is not in line with a lunar cataclysm. Just one thing we need to keep in mind is that we still then have a discrepancy with the absolute model ages, not for Serenitatis, then they add up quite well. But if this is indeed the Crisium age, then it would be a discrepancy to Chilla's absolute model age, or maybe it is indeed Nectaris, and then we're quite in a similar area of ages. And thank you for your attention.